Hey guys, welcome back. We are about to go through Griffiths section 1.3 of chapter 1 of his quantum mechanics book. And that deals with probabilities. And so in this first video, we are just going to be going over discrete or probability of discrete variables as opposed to the probability of discrete and continuous variables. So let's first talk about what is the difference between discrete variables and continuous variables. So discrete variables are variables that have a finite or countable value of numbers. So this means you can write a list of these numbers. So if I have a pocket full of change, let's say I have 2 pennies, a dime, and or not a dime, a nickel, and then 3 dimes. Right here, I can easily write these all out, and there can't be numbers in between the 1 and the 5, because at least in U.S. currency, there's no cent value between those, and there's no cents between 5 and 10. But continuous variables are different, so they are variables that have an infinite or uncountable number of values. So you usually write this as a range of values. So let's say it can be anything from 0 to 5. So whatever our value is, it could be, say a 1.25968, random series of numbers. And then the next number would just be 25968 and some more numbers. It could be infinite variations of almost an identical number. So there's an infinite number inside of here, while there's only a finite number inside of here. That's really the difference between those two. And so if you want some examples of discrete variables, so obviously change or money is an example, the number of students in a class, something like that. While continuous variables, if we're thinking of physics, we can think of the position or velocity as being things that could have any number of values. Now, if you go super deep into physics, it's is the universe discrete or continuous? I'm pretty sure there's an argument going on there. But for these purposes, we're just going to treat things like velocity as or position of a free body as continuous. So now let's go on to some of our notation that we'll be using. So we're going to use J just to label the things in our list. Let me go here. So J, example, if we go back to our coins, if we have 1, 1, 5, 10, 10, I think there was another 10, but don't worry about that. J would be 1 or 5 or 10 in this example. Right, it's just the label that we're giving our change. So instead of writing penny, penny, nickel, dime, dime, we're writing the value of those coins. And then the next thing you'll see is N of J. So N of J just really tells you how many of those J's you have. So if we say N of 1, so how many pennies do we have? Well, we got 2 pennies up in our list. N of 5, we've got 1 nickel in our list, and then N of 10, say we got, we have 2 dimes. So N of whatever just tells you how many of whatevers you got. And so these are really the building blocks. I would say these two, or let me use a different color. These two words or notations are the building blocks of probability, or at least for discrete probability. And next we get into the total number of elements. So that's just when you count up your list. So we have 1, 2, 3, 4, 5. It's just how many things we have in our list. And obviously, N is just going to equal to the sum from J equals 1 to infinity of N of J. Now, obviously, we don't have values of J equals 2. But that just means that N of 2 is equal to 0. So when we add these all up, we get 2 plus 0 plus 0 all the way till we get to 5, plus 1, plus 0, plus 0, all the way till we get to 10 again, we get plus 2. And then we see 2 plus 1 plus 2, that does equal 5. So this is a good definition for the total number of elements. And that's what Griffiths uses, and everyone else uses it because it's a true fact. So we got this done now. So the next thing is defining what we mean by probability. So the probability of randomly selecting a jth element out of our list is equal to the total number that we have of j's that we have in that list divided by the total number of j's. So for example, if we want to find the probability of selecting a nickel out of our list, this is going to be n of 5 divided by n. And in a case up here, we see n of 5. Oh, there's only one of them, so 1 divided by, and we have a total of 5 elements, 5. We have a 20% chance of picking a nickel out of our list. And so the next thing to really illustrate or to think about is the fact that probabilities are normalized. And what we mean by normalized, that means like regardless of what our probability function is, so sum of p of j, regardless of what this is, this sum will always equal 1, just off of how we define p of j to be. So the proof of this is that sum j equals 1 to infinity. We define p of j to be n of j divided by the total number. Since this n is a constant, it can come outside of our summation, and we would get 1 divided by n times the sum from j equals 1 to infinity of n of j. And now we can see that this sum right here is just the definition of n. So rewriting this is equal to 1 divided by n times n, so this is indeed equal to 1. We proved this statement. We proved it. But what does it mean? So when we add up our probabilities, let's say like, all right, we want to know what's our chance of getting p of 1, right? Say we want to know, if we put our hand in there, if we pull out a penny, or let's say we pull out a nickel, we would have to add those two probabilities, and that would be 2 over 5 plus 1 over 5, which is equal to 3 over 5. You see, this isn't 100% because we have the option or the ability to pull out other values besides 1 and 5. But we were to add all of our probabilities together, we see this equals to 5 out of 5. So we have to pick one of these three values. So that's just normalization means that we are truly considering all of the variables or all of our options. Right? So if we, are working through a problem and we do our integral so when we go to continuous, our sum is going to be replaced with integrals. And we do the integral from negative infinity to infinity of what we think is our probability density function or probability function, and it's not equal to 1, that would definitely indicate to you that this is not your probability density function because it doesn't include all your variables. And usually that won't happen, but I mean, if that does happen, you can say, oh, this isn't even a probability density function. This is useless. So now that we've talked about probability and normalizing it, let's go on to some statistical terms. So one term you'll often see is most probable. So if you're dealing with discrete values, you'll probably have, you can actually click on a marker. We probably have a graph, and it's going to be a histogram. So let's say 1, 5, and 10 for our list example. 1, 2. And we had possibility of getting 2 pennies. Actually, let's kind of alter our list to make this more example. So we have 1, 1, 5, 10, 10. Let's say we're dealing with this list of stuff. We have 1 5, and then we have 3 dimes. Okay. We can see that the most probable is the value with the highest P of j. And, over here, make this actually P of j. Over here, we have our possible values of P of j, and we see that, we have the highest probability of selecting a dime because its P of j is the largest. That's what they mean by most probable. Okay, so the median is simply just the middle value. So you can think about back to like elementary school when you're finding median values. You just subtract one element from each side till you get to the middle. And this is one of those weird cases where you have an even number thing. So I believe in most cases, whenever you have a median and you are dealing with discrete values, and you get to one where there's like no real median, you could either list this as 5 or 10, or you can do the average of those two, 5 plus 10 divided by 2, which is going to give us 7.5, right? So I think these are two valid ways to list what the median would be in this case. And the general formula for the median is going to be the total number of elements that you have, so big N plus 1, divided by 2. This will land you to the middle position. If you have like an odd number, it will give you the exact number that you're on, or the exact number that is your median value. Or if you have an even number, it will get you to they'll take you to the left of value. So in this case, it would give us 5. Okay, so now let's move on to the most important, I would say, statistical term that we'll be dealing with in quantum mechanics is the average value, also known as the mean. And in quantum mechanics, very often referred to as the expectation value of a set of variables or a set of values. And this is the value that you would select if you were to randomly select out of a bag multiple times. This would be the average value you get. And so mathematically, we write this as expectation value of j is equal to the summation of j times n of j divided by capital N. And if we were to simplify this, this has a very nice form of the summation of j times P of j, because remember, capital N of j divided by capital N is just P of j. And this can be generalized to any function of j. This is going to equal to the summation of f of j times P of j. Very important functions to remember. And then I think this brings us to our final portion of discrete probabilities, and that is going over the variance or standard deviation. So the variance and standard deviation they essentially tell you how far apart your data is spread. So let's draw a graph really quick. I think most people will probably understand it. So say here is our mean value. And so if we have, for discrete values, let's say it looks like something like this. Alright, so that's set 1. And then set 2 just looks like. Right, so we can see that this data is spread, the set 1 values are spread out much more from the mean than the set 2 values are. And so we measure that with what's called the variance. And so the variance, we write that as sigma squared is equal to the average of j minus the average of j squared. So also, I don't think I made it clear, but let me actually emphasize this. We represent the average value of something with these brackets. And oftentimes in quantum mechanics, you'll see these as bra. So this, what this side is representative of, and then ket. And when you add these two together, you get bracket. But that's what, when we write a variable inside of these brackets, we mean the average. So if we go back to this right here, we're taking the average of the difference between a random point j minus the average of j. And so the variance can be generalized again to be equal to f of j minus average of j, or f of j, all of that squared, right? But anyways, that's what the physical meaning of j minus the average of j will give us. It's just the spread. And we can simplify this. Griffiths goes through the proof of this, but the variance simply just be written as the average of j squared minus the average of j squared. It sounds the same, but these are different quantities. So let's move on. Actually give ourselves some little more room to write this. So variance is the average of j squared minus the average of j squared. And if you were to write this out, this looks like j squared times p of j minus the sum of j times p of j squared. So you see that these are very different quantities. And one thing about the variance is that it will always be positive. So that means that this term right here is always going to be greater than or equal to 0. So that tells us that the sum of j squared times p of j is going to be greater than or equal to the sum, the sum of j times p of j, all of that squared. It's an important important result, not important, but kind of interesting result that comes out of this. And then the standard deviation, something you're probably way more familiar with than the variance, is just the square root of the variance. So the standard deviation is going to equal to the square root of the average of j squared minus average of j squared. Okay, so I hope this was somewhat useful, and it'll become more useful once it's actually applied. So I'm going to be doing some videos where we actually practice calculating the variance, the mean, or the variance, mean, standard deviation, and things like that for discrete values. Anyways, I hope this was helpful, and I will be coming out with another video on continuous probability.